October 18th, 1940. The passenger liner SS Excambion docked at New York Harbor in the pale morning light, carrying refugees from a Europe already consumed by Hitler's war machine. Among the 317 passengers who disembarked that morning stood Heinrich Mohaupt, 25 years old, Swiss by birth, carrying a single, battered leather satchel and a secret that would change the nature of armored warfare forever. The crossing from Lisbon had taken 17 days. 17 days of watching the Atlantic horizon for German U-boats that never materialized. 17 days of wondering if he would reach America before his invention became irrelevant, before some other inventor discovered the same principles he had painstakingly developed over 5 years of experimentation. Inside that satchel lay technical drawings for a shaped charge anti-tank grenade that had already been rejected by British ordnance officials as too expensive, ignored by Swiss military authorities as impractical, dismissed by French generals as theoretically interesting but tactically useless. And yet, the device possessed a capability that would soon terrify German tank crews across 3 continents, fundamentally alter infantry tactics, and spawn an entirely new class of weapons. The drawings showed something deceptively simple. A cone of copper metal, precisely machined to a 42-degree angle, pressed inside a hollow explosive charge with careful attention to standoff distance and cavity geometry. Just copper and explosive, configured in a way that seemed almost elementary once you saw it. But what that copper cone could do when detonated defied everything military engineers thought they understood about how to defeat armor. It wasn't kinetic penetration, the brute force approach of firing heavy projectiles at high velocity that had dominated anti-tank weapon design since the first tanks appeared on the Western Front. It wasn't simply explosive force, the crude method of using raw blast power to crack armor plate that had proven marginally effective at best. It was something else entirely, something that seemed almost magical until you understood the hydrodynamics, something that would make a hand-thrown grenade more effective than a 37mm anti-tank gun. Mohaupt had spent the previous 5 years demonstrating his invention to skeptical military officials across Europe, traveling from Zurich to London to Paris to Bourges, watching as they examined his test results with expressions ranging from impressed fascination to suspicious dismissal. The British had been the first. Back in early 1939, just months before war erupted, he'd travelled to the Royal Arsenal at Woolwich, the heart of British ordnance development, where engineers had been wrestling unsuccessfully with shaped charge technology for years. The demonstration had taken place on a grey March morning. Typical London weather. Rain threatening, but never quite arriving. Heinrich had set up his test charge in a fortified testing pit, positioned it exactly 90 millimeters from a steel plate representing the armor of a Matilda infantry tank, and explained through an interpreter what he expected to happen. The British engineers had listened politely, their faces revealing nothing, their questions probing for weaknesses in his theoretical framework. Then he detonated the charge. The explosion was unimpressive, a sharp crack rather than a dramatic blast, producing none of the pyrotechnic spectacle that observers expected from anti-tank weapons. But when they examined the target plate, they found a hole punched clean through 50 millimeters of hardened steel, the edges showing the characteristic smoothness of hydrodynamic penetration rather than the ragged tearing of conventional explosive attack. The British engineers had been impressed, certainly. The penetration was undeniable, the implications obvious. But when Mohaupt had explained that his copper liner design was patented, that he expected licensing fees for what he considered a revolutionary innovation rather than an incremental improvement, the British enthusiasm had cooled dramatically. They'd suggested, politely but firmly, that the shaped charge effect was already known, had been documented by American physicist Charles Monroe back in 1888, that adding a metal liner was merely an optimization rather than a fundamental breakthrough. The fact that nobody had made it work effectively until Mohaupt added the copper liner seemed to British procurement officials beside the point. They'd offered him £500 for his patent rights, a sum that barely covered his travel expenses from Zurich, and expressed surprise when he refused. His insistence on proper compensation, on recognition that his specific innovation of the copper cone was what made shaped charges militarily useful, had been interpreted as greed rather than reasonable business practice. The Swiss had been worse, if such a thing was possible. Mohaupt had demonstrated his invention to Swiss military authorities in September 1938, hoping that his own country would recognize the value of technology developed by a Swiss citizen. The demonstration had gone perfectly, conducted at a military testing facility outside Zurich. The test plate had been penetrated cleanly, the measurements had been documented, the implications for anti-tank warfare had been explained. But Swiss military doctrine, conservative and traditional, held that only kinetic penetrators, projectiles fired at high velocity from rifled guns, could effectively defeat modern tank armor. Shaped charges were laboratory curiosities, they'd told him. Interesting physics, but impractical for battlefield application. The Swiss army would continue developing its excellent anti-tank rifles and towed anti-tank guns. Thank you very much. The French had shown more interest, at least. Initially, Mohaupt's father, Berthold, also an inventor in the munitions field, had connections to French weapons engineer Edgar Brandt, a prominent figure in French armaments industry. Through Brandt's support and intervention, Heinrich had managed to file his patent in France on November 9, 1939, just 2 months after the war began. Brandt had even secured exclusive marketing rights for France in exchange for his assistance, promising to develop and manufacture Mohaupt's shaped charge grenades for the French military. For a brief period, it had looked like France would be the first nation to properly exploit Heinrich's discovery. Demonstrations took place at the military testing grounds in Bourges on February 18, 1940, and again at Sattery near Versailles on June 10. French ordnance officials were enthusiastic. Production preparations began. Then the German invasion swept through the Low Countries and into France, and Edgar Brandt's carefully laid plans collapsed along with French military resistance. The armistice was signed on June 22. Brandt's manufacturing facilities were scattered across occupied and unoccupied zones, his workers dispersed, his equipment frozen by military occupation. Mohaupt and his father had spent desperate weeks trying to evacuate equipment to the unoccupied zone in Pau. But the chaos of France's collapse made organized weapons development impossible. By October, Heinrich had fled to Portugal, waiting for American visa approval, while German forces consolidated their grip on Western Europe and prepared for an invasion of Britain that would never materialize. Portugal had been a strange interlude, 3 months of waiting in Lisbon while bureaucracy ground through the process of approving his entry to the United States. He'd spent the time refining his drawings, improving his calculations, preparing for what he hoped would be his final demonstration to his final potential customer. If America rejected his invention as too expensive or impractical, Heinrich would have nowhere else to turn. The Soviet Union was technically an ally of Germany through their non-aggression pact. The British had already declined to pay fairly. Switzerland wanted nothing to do with unconventional weapons. France was occupied. America was his last hope. Now, finally, he stood on American soil with one last chance to convince a major military power that his copper liner innovation could change the war. Paul de Lalande, a French military emissary who had arrived weeks earlier, bearing reports about Mohaupt's successful demonstrations, had arranged the meeting at Aberdeen Proving Ground. The American military, desperate for effective infantry anti-tank weapons after watching German panzers sweep through Poland and France, had agreed to observe. But Mohaupt had learned to temper his expectations. He'd been disappointed too many times before to allow himself optimism. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The discovery itself had come 5 years earlier, in late 1935, during experiments in his father's workshop in Zurich. Heinrich had been 20 years old, working as his father's assistant while studying chemical engineering at the local technical institute, when he'd stumbled upon something that would define the rest of his life and revolutionize anti-tank warfare. The shaped charge effect itself wasn't new. Scientists had known since the late 19th century that explosives with hollow cavities produced enhanced penetration against targets, what researchers called the Munro effect after its most famous documenter. Charles Munro, at the U.S. Naval Academy, had published detailed observations in 1888 describing how explosive blocks with hollowed-out cavities could produce remarkably deep impressions in steel plates. German scientist Egon Neumann had rediscovered it independently in 1910, conducting his own series of systematic experiments. The German explosives company Weissag had even patented the concept in 1911, proposing military applications that were never actually developed. But all these earlier discoveries had produced only modest penetration improvements, interesting from a physics standpoint, but nowhere near enough to defeat modern tank armor. A hollow charge might penetrate 10 or 15 millimeters deeper than a solid charge of the same size. Useful for demolition work, perhaps, but inadequate for anti-tank warfare where armor thicknesses were approaching 30 or 40 millimeters on even light tanks. What nobody had figured out was the metal liner. The breakthrough came during one of Heinrich's experiments with different cavity configurations. He'd been testing hollow charges lined with various materials, trying to understand why some cavity shapes worked better than others, why conical cavities seemed to produce deeper penetration than hemispherical ones, why the angle of the cone affected results in ways that didn't quite match theoretical predictions. Most of his tests used steel liners because steel was cheap, readily available from local scrapyards, and easy to form into the shapes he needed. The results were disappointing. Penetration depths barely exceeded what unlined charges achieved. Sometimes the steel liner seemed to actually reduce effectiveness, fragmenting into particles that dissipated energy rather than focusing it. Heinrich had begun to suspect that metal liners were a dead end, that the Weissag patent had explored a promising idea that simply didn't work in practice. Then he tried copper. Not because he had any theoretical reason to expect copper would work better than steel or aluminum or brass, but simply because he had copper sheet available in the workshop, left over from an electrical project his father had completed, and wanted to test whether liner material mattered at all before abandoning the concept entirely. He'd formed the copper into a crude cone using a simple stamping die, pressed it into the explosive charge with the same geometry he'd been using for steel tests, and detonated it against a test plate, expecting results similar to what he'd seen before. The difference was astounding. Dramatic enough that Heinrich initially thought he'd made a fundamental measurement error. Where steel liners had produced penetration holes of perhaps 30 or 40 millimeters, the copper liner punched through nearly 80 millimeters. He'd repeated the test using a fresh piece of steel plate to ensure the first hadn't been defective. Same result. He'd checked his explosive composition to make sure he hadn't accidentally mixed a stronger batch. No difference. The copper liner was producing penetration depths that exceeded anything documented in the scientific literature by a factor of 2 or more. It took him months of careful experimentation to understand why. Copper possessed a unique combination of properties that made it ideal for shaped charge applications. High density, similar to steel at approximately 9 grams per cubic centimeter, which meant the copper jet carried substantial mass and momentum. Exceptional ductility, the ability to deform plastically without fracturing, which allowed the copper to form a coherent jet rather than fragmenting into particles. Relatively low melting point, just over 1,000 degrees Celsius, which meant the copper could partially liquefy during the jet formation process. When the explosive detonated, it compressed the copper cone inward and forward at tremendous velocity, perhaps 2,000 meters per second. The copper, being ductile, didn't shatter into fragments like steel or iron would. Instead, it deformed smoothly into a narrow jet of metal, traveling at velocities approaching 8 kilometers per second at the tip, with the slower-moving tail section following behind at perhaps 3 or 4 kilometers per second. That jet, moving at hypersonic speeds far exceeding anything achievable through conventional gun propulsion, interacted with the target armor through hydrodynamic principles rather than simple kinetic impact. At those velocities, both the jet and the armor behaved like incompressible fluids, Despite being solid metal at normal temperatures and pressures, the copper jet would penetrate through a process of continuous erosion, pushing aside armor material through sheer pressure as it maintained its coherence over distances of 10 or 15 cone diameters. Steel liners, by contrast, tended to fragment prematurely, breaking up into particles that couldn't maintain the sustained penetration necessary to defeat thick armor. Heinrich had spent the next 3 years, from late 1935 until early 1939, refining every aspect of the geometry. The cone angle mattered enormously. He discovered too shallow, below 35 degrees from the axis, and the jet formed slowly, losing penetration capability because the copper slug that formed at the rear of the jet became too dominant, too steep, above 50 degrees, and the jet formed quickly but fragmented prematurely, breaking up before penetrating deeply. He'd settled on 42 degrees as optimal for most applications, a compromise that maximized both jet velocity and coherence. The standoff distance, the gap between the cone's apex and the target surface, proved equally critical through mechanisms that weren't immediately obvious. Too close, less than 2 cone diameters, and the jet didn't have enough distance to form properly, still consisting of partially formed copper rather than a fully developed jet. Too far, more than 6 or 7 cone diameters, and the jet would begin to break up before impact, losing the coherence necessary for deep penetration. For his 30mm grenade, he determined through systematic testing that a standoff of approximately 3 cone diameters, 90mm, produced maximum penetration. The thickness of the copper liner required careful calculation as well. Too thin, less than 1% of the cone's base diameter, and the jet lacked mass to sustain penetration through thick armor, pinching off after only a few centimeters. Too thick, more than 2%, and the cone wouldn't collapse efficiently during detonation, wasting explosive energy on moving excess copper mass rather than accelerating it to maximum velocity. He'd arrived at a liner thickness varying from approximately 1.4% of the base diameter at the apex to 1.6% at the base as optimal, creating a slight taper that improved jet formation. The explosive itself mattered, though perhaps less than Heinrich had initially expected. Higher detonation velocity produced better results, which meant military-grade explosives like TNT, PETN, or RDX were preferable to commercial dynamite or black powder. But the difference between TNT at approximately 6,900 meters per second and PETN at approximately 8,400 meters per second was less significant than he'd anticipated, perhaps 15 or 20% improvement in penetration rather than the 40% difference in detonation velocity. All of this knowledge, painstakingly developed through hundreds of tests, through thousands of precise measurements, through systematic variation of every parameter he could imagine, through failures and dead ends and occasional inspired guesses, was contained in the drawings Heinrich carried in his leather satchel. Knowledge that the British thought wasn't worth paying for. Knowledge that the Swiss considered impractical. Knowledge that the French had been willing to exploit but were now unable to develop. Knowledge that he desperately hoped the Americans would recognize as revolutionary and compensate fairly. The demonstration at Aberdeen Proving Ground took place on October 23, 1940, just 5 days after Mohaupt's arrival in America. The morning was cold, unseasonably cold for Maryland in October, and Heinrich's hands shook slightly as he unpacked his test equipment in the fortified testing area. Whether from the cold, or from nerves, or from the accumulated tension of 5 years of rejected demonstrations, he couldn't tell. This felt like a final examination, pass or fail, with no opportunity for retakes. Colonel Leslie Skinner stood 40 yards away, behind a concrete blast wall, arms crossed, watching with the undisguised skepticism of a man who'd seen too many inventors promising revolutionary weapons that failed spectacularly when subjected to actual testing under realistic conditions. Skinner commanded the Army's rocket development branch at Aberdeen, having transferred from artillery service 2 years earlier specifically to develop battlefield rocket applications. His experience with rocket propulsion went back to Robert Goddard's pioneering work during World War I. He understood explosive physics at an intuitive level that few officers possessed, could calculate blast effects and fragmentation patterns in his head while standing at a testing range, which made him harder to impress with fancy claims, and more dangerous if he decided Mohaupt was a fraud or a fool. Beside Skinner stood Captain Edward Oule, younger by 15 years, more open-minded but equally skeptical after evaluating a dozen impractical anti-tank weapon proposals in the past 6 months. Oule had been assigned to develop infantry anti-tank weapons that could be carried and operated by regular infantrymen rather than specialized crews, and he'd already rejected proposals ranging from shaped charge hand grenades that were too heavy to throw to rocket-propelled projectiles that couldn't hit barns at 50 yards. A hand grenade that could penetrate tank armor sounded like yet another inventor's fantasy, the kind of claim that collapsed under actual testing when faced with real armor moving at combat speeds rather than stationary test plates in ideal conditions. Also present were 3 civilian engineers from DuPont Chemical Company, the firm that had manufactured the explosive charge for Mohaupt's test grenade, and 2 officers from Army Ordnance Headquarters in Washington who would ultimately decide whether to purchase patent rights and develop the weapon for production. Paul Delalande, the French emissary who had arranged the demonstration, stood slightly apart from the American observers, his expression mixing hope and anxiety in equal measure. Mohaupt's test grenade looked crude, almost amateurish, compared to the precision-engineered weapons the Army was accustomed to evaluating at Aberdeen. 30 millimeters in diameter, it resembled a stubby can with fins attached, its nose containing the copper cone liner that Mohaupt insisted was the key to the entire design. The body was simple sheet metal, formed and welded with techniques that any competent metalworker could replicate. The fins were cut from aluminum plate and riveted on. The whole device had an improvised workshop prototype appearance that didn't inspire confidence in observers used to seeing polished military hardware. The explosive charge consisted of a mixture provided by DuPont, pentolite, a combination of PETN and TNT that provided high detonation velocity with good stability and reasonable manufacturing safety. 8 ounces of it, roughly 227 grams, surrounded the copper cone in a carefully calculated configuration. The entire device weighed just 700 grams, light enough for a soldier to carry dozens without excessive burden, light enough to throw if necessary, though nobody would actually want to throw it the distances needed for safe combat employment. The target was a steel plate, representing typical German tank armor, 50 millimeters thick, rolled homogeneous armor of the type used in Panzer Mark III medium tanks, and the side armor of Panzer Mark IV tanks. The plate had been positioned vertically on a reinforced steel frame, with sandbags behind it to catch fragments and measure penetration depth. Mohaupt had specifically requested the plate be positioned exactly 90 millimeters from the grenade's position, measured from the apex of his copper cone to the face of the armor, a distance of 3 times the diameter of his shaped charge cavity. The standoff distance, he'd explained through his heavily accented English while positioning the equipment, mattered almost as much as the cone's geometry. Too close, and the copper jet wouldn't fully form before impacting the armor, reducing penetration. Too far, and the jet would begin to break up in flight before reaching the target, fragmenting into particles that couldn't sustain deep penetration. 90 millimeters was optimal for his 30 millimeter charge. Larger charges would require proportionally larger standoffs. Skinner had nodded, made notes in his leather field book, but Heinrich could see the skepticism hadn't diminished. Standoff distance was a detail that laboratory researchers worried about when trying to achieve maximum performance under controlled conditions. Combat weapons needed to work across a range of conditions, not just at precisely measured distances. A grenade that only worked when detonated exactly 90 millimeters from the target would be useless in battlefield employment. Heinrich attached the electrical detonator to his test grenade, a simple blasting cap that would initiate the pentolite charge when current flowed through its bridge wire. He ran the firing wires back to a protected position behind the blast wall, spooled out 30 meters of twisted copper conductor, and connected them to a battery-powered firing box. The assembled observers, perhaps a dozen army officers and civilian engineers, plus Delalande, took positions behind the concrete barrier that Aberdeen engineers had built specifically for testing potentially dangerous experimental weapons. Heinrich joined them, his thumb hovering over the firing button mounted on the wooden box, feeling the weight of 5 years of work concentrated into this single moment. If the demonstration failed, if the charge produced disappointing penetration, or if American officials decided the technology wasn't worth purchasing, he would have nowhere else to turn. His patent rights in Europe were frozen by war. His reputation among military procurement officials was already damaged by rejections from Britain and Switzerland. This was his last opportunity to prove that his copper liner discovery was revolutionary rather than merely interesting. "Gentlemen," he said, his Swiss-German accent making the English feel clumsy and foreign in his mouth, "what you will see does not look impressive. No large explosion, no dramatic fireball, no fragments flying everywhere. But please, I ask that you examine the target plate carefully afterward. The penetration is what matters, not the show." He pressed the button. Electrical current flowed through the wires, heated the bridge wire in the blasting cap to incandescence in a fraction of a second, initiated the primary explosive in the cap, which detonated the pentolite charge. For a fraction of a second, nothing visible happened to external observers. Then came the explosion. Oddly quiet, compared to what Skinner and the other observers had expected based on experience with conventional explosives. No dramatic fireball lighting the testing area, no earth-shaking concussion rattling equipment, no shower of fragments peptering the blast wall, just a sharp crack, almost like a large-caliber rifle shot, accompanied by a puff of grey-white smoke that dissipated quickly in the October breeze. Several of the observers looked disappointed, exchanging glances that clearly communicated their assessment that the test had been a failure. The weapons they were used to evaluating at Aberdeen, artillery shells and demolition charges and conventional anti-tank munitions, produced impressive pyrotechnic displays, massive fireballs, thunderous detonations that could be heard miles away. This looked like a dud charge, an explosive that had only partially detonated or had failed to function as designed. But Mohaupt was already moving toward the target plate with quick steps that suggested neither disappointment nor triumph, just patient expectation of what he knew would be there. His expression remained neutral, giving nothing away. Skinner followed, his longer stride bringing him to the plate first, and stopped abruptly 2 meters away. The entry hole was perhaps 20 millimeters across, at the surface, clean-edged and circular, showing none of the ragged tearing and deformation that conventional explosives produced when they attacked armor. The edges were smooth, almost machined-looking, with a slight lip where the copper jet had pushed material inward during penetration. But what made Skinner's breath catch, what caused him to forget his professional skepticism, for a moment, was that he could see completely through the 50-millimeter plate. The copper jet had punched through and continued into the sand backstop beyond, creating a hole that extended an unknown depth into the packed earth. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Captain Ohl arrived a moment later, pulled out a brass measuring tape from his field kit, and began documenting the hole's dimensions with careful precision learned from years of ordnance testing. Entry diameter, 20 millimeters, exit diameter, 30 millimeters, complete penetration through 52 millimeters of hardened armor plate. The exit hole was larger than the entry, consistent with the jet expanding slightly as it completed penetration, which indicated the copper stream had maintained coherence through the entire thickness of the plate rather than fragmenting halfway through. Uhl examined the sand backstop, carefully excavating the area directly behind the target plate. The copper jet had continued perhaps another 30 or 40 millimeters into the sand before losing coherence and depositing the remains of the jet as copper residue. Total penetration depth approaching 90 or 100 millimeters, from a 30-millimeter charge weighing 700 grams. The numbers didn't seem possible. "How?" Skinner asked, the single word containing volumes of professional curiosity mixed with disbelief and the beginning of understanding that he was witnessing something genuinely revolutionary rather than incrementally better than existing technology. Mohaupt gestured to the scattered remains of his test grenade, now distributed across the testing area as fragments of sheet metal and bent aluminum fins. The copper liner. When the explosive detonates, it compresses the copper cone at extremely high velocity. The cone collapses inward and forward, forms into a jet of copper metal, traveling perhaps 7 or 8 kilometers per second at the tip, slower at the tail. At such velocities, the copper behaves like a liquid, not a solid. It flows through the armor like water through paper. 7 or 8 kilometers per second, Uhl repeated, doing the mental arithmetic and coming up with numbers that seemed impossible. "That's faster than any rifle bullet we've ever measured, faster than most artillery shells leave the barrel. How can a jet of copper achieve those velocities from a stationary explosive?" "The shaped charge concentrates the explosive energy," Mohaupt explained, gesturing with his hands to illustrate the collapse mechanism. "Instead of pushing equally in all directions, the hollow cone focuses energy inward and forward. The copper accelerates to extreme velocity over very short distance, only a few millimeters, but sufficient to create hydrodynamic penetration." "Hydrodynamic," Skinner said, testing the unfamiliar term. "You're saying the copper and the steel both behave as fluids?" "At these velocities and pressures, yes, the impact pressure exceeds the yield strength of both materials by orders of magnitude. They flow past each other. The jet continues penetrating as long as it maintains coherence. Copper's ductility allows formation of a jet that stays together much longer than steel or iron. Steel liner fragments, copper liner flows. That is the critical difference." Skinner examined the test setup more carefully, noting the precise positioning, the careful geometry, the attention to every detail of spacing and alignment. "You said 30 millimeters. This grenade is 30 millimeters in diameter, and it penetrated 50 millimeters of armor, plus additional depth into the backstop." 52 millimeters through the plate, Uhl corrected. "Call it roughly 100 millimeters total before the jet broke up." "More than 3 times the charge diameter," Skinner calculated aloud. "What happens if you make it larger? 60 millimeters? 75? Does the penetration scale linearly?" Mohaupt allowed himself a small smile, the first expression of satisfaction he'd permitted since arriving at the testing ground. "Approximately, yes, perhaps not perfectly linear, but close. A 60-millimeter charge should achieve 150 millimeters, maybe 160 millimeters of penetration if the geometry is optimized correctly. A 75-millimeter charge, 200 millimeters, maybe more." The implications hit Skinner with the force of revelation. 150 millimeters was 6 inches. 200 millimeters was 8 inches. That was enough to penetrate the frontal armor of any German tank currently in service, enough to defeat even the thickest armor on the new Tiger tank that intelligence reports suggested was entering production. And it could be accomplished with a weapon small enough for an infantry soldier to carry and employ. An infantry soldier, armed with a launcher capable of projecting a 60-millimeter shaped charge grenade at useful ranges, 200 or 300 meters, would have the power to destroy German Panzer Mark IV tanks that currently required specialized towed anti-tank guns or self-propelled tank destroyers to engage effectively. The entire structure of anti-tank defense, built around emplaced guns and defensive positions, could be revolutionized by portable-shaped charge weapons that gave every infantry squad tank-killing capability. "Colonel Skinner," Uhl said quietly, his voice controlled but urgent, We need this technology. Whatever this gentleman wants, whatever it costs, whatever licensing fees or royalties or recognition he expects, we need this immediately. This changes everything about infantry anti-tank. Doctrine. Skinner nodded slowly, his mind already racing through the logistics of development and production, but his experienced eye, trained by decades in army procurement and weapons development, was already noting potential problems. The copper liner. Copper was expensive, in increasingly short supply, as electrical demand grew with military mobilization, needed for electrical wiring in aircraft, ships and vehicles, needed for artillery shell-driving bands that sealed propellant gases, needed for radio equipment, fire control systems and communications networks, needed for 1,000 different military applications. Could they produce enough copper liners for mass production of shaped charge grenades? Would procurement officials approve the cost when steel might work almost as well? The negotiations that followed over the next 3 weeks, through November 1940, revealed something uncomfortable about military procurement and bureaucratic decision-making, even in wartime. When Mohaupt explained in technical briefings that his copper liner discovery was the specific innovation that made shaped charges militarily effective, that experiments with steel or aluminum or other metals produced significantly worse penetration, Army ordnance officials suddenly became cagey about compensation and patent rights. They pointed out, with lawyerly precision and careful documentation, that the shaped charge effect itself had been known since Monroe's experiments in 1888, that the hollow cavity principle was documented in German patents from 1911, that various researchers, including R.W. Wood at Johns Hopkins University, had conducted shaped charge experiments in the 1920s and 30s. An American inventor named Neville Hopkins had even submitted a shaped charge design to the Ordnance Department. Earlier in 1940, they told Mohaupt. The Army had rejected Hopkins's proposal, citing that old Wasag patent, claiming it wasn't new technology. But now, with Mohaupt's demonstration proving the concept worked spectacularly under field conditions, perhaps the Army should reconsider Hopkins' design. Perhaps Mohaupt's contribution was simply optimization of a known technique rather than fundamental innovation. Perhaps his expected licensing fee of $20,000, calculated based on the revolutionary nature of making shaped charges actually work against tank armor, was too high given that the underlying physics were already documented. Mohaupt found himself in an impossible negotiating position. He held French and Swiss patents on his copper liner innovation, dated to November 9, 1939, but he was a foreign national in a country preparing for war, negotiating with military officials who could simply classify his invention as militarily significant and exclude him from further involvement under national security grounds. His expected fee of $20,000, entirely reasonable, for a patent that would revolutionize anti-tank warfare and save thousands of American lives, suddenly became negotiable downward when Army procurement discovered it could claim the underlying principle was already known to science. The compromise, reached in late November after weeks of increasingly frustrating negotiations, gave Mohaupt a fraction of what his invention was worth, $7,000 rather than $20,000, no royalties on production weapons, no guarantee of continued involvement in development, no recognition beyond a consulting contract that explicitly stated he was advising on optimization of existing technology rather than introducing revolutionary new concepts. And then, on June 4, 1941, the Army classified the entire shaped charge program under wartime security regulations. Heinrich Mohaupt, foreign national, despite his pending American citizenship application, was thanked politely for his contributions and formally informed he could no longer participate in the development of weapons based on the technology he had invented. He would be retained as a consultant on peripheral projects, they assured him. But the actual engineering work, the refinement of charge geometry, the development of production techniques, the integration of shaped charge warheads into rocket projectiles, all of that would proceed without his direct involvement. The cruel irony wasn't lost on Mohaupt as he sat in his small Washington apartment that evening, reading the formal letter that effectively ended his participation in the program. His invention was deemed too valuable to compensate him properly for, too important to ignore, but too sensitive to let him help perfect. He'd spend the rest of the war working peripheral projects, consulting on demolition charges and oil well fracturing techniques, watching from the outside as American engineers took his copper liner discovery and built an entirely new class of anti-tank weapons around it. February 1942. Technical Sergeant Frank Morrison stood in the cavernous manufacturing facility of General Electric's Bridgeport plant in Connecticut, watching the first production run of something called the M6 anti-tank rocket roll down an assembly line that stretched the length of 2 football fields. The factory floor hummed with coordinated activity, hundreds of workers at dozens of stations installing components, testing assemblies, packaging finished rockets in wooden crates marked with cryptic ordnance codes. The sheer scale of production was staggering for a weapon that most soldiers had never heard of, that wouldn't see combat for another 9 months. Morrison had transferred from artillery maintenance at Fort Sill specifically to work on this project, leaving behind a comfortable assignment teaching gun crews how to service 75mm pack howitzers. The transfer order had been marked Priority 1, suggesting the importance of whatever program he was joining. The recruiting officer had told him it was the highest priority weapon development of the war, that it would give American infantry the power to stop German panzers with equipment light enough for a single soldier to carry and employ, without specialized training. What they hadn't told him, what nobody seemed willing or able to explain in terms a practical machinist could understand, was how the damn thing actually worked. And Frank Morrison hated not understanding the weapons he helped build. His father had been a machinist before him, had taught young Frank to read engineering drawings before he'd learned to read storybooks, had instilled in him the fundamental belief that understanding how something worked was the essential first step to making it work reliably in the hands of soldiers who would depend on it for their lives. Now Frank stood in the middle of the largest production facility he'd ever seen, surrounded by workers building weapons based on physics that seemed almost magical, and nobody could give him a straight explanation that made mechanical sense. The copper cones arrived from a specialized metalworking facility in Bridgeport, each one precisely machined through a multi-stage process involving blank stamping, deep drawing, and precision forming operations. The engineering specifications demanded tolerances measured in thousandths of an inch, tighter than many rifle barrels, tighter than aircraft engine components. Each cone was inspected 3 times during production, measuring wall thickness at multiple points, verifying the cone angle with precision gauges, checking surface finish to ensure smooth internal surfaces free of scratches or tool marks that might disrupt jet formation. Too shallow an angle, 38 or 39 degrees, instead of the specified 42, and the penetration dropped by 30% according to test data. Too steep, 45 or 46 degrees, and the copper jet would fragment prematurely, breaking into particles that couldn't sustain penetration through thick armor. The thickness of the copper had to fall within specifications, varying from 1.2 millimeters at the base to 0.8 millimeters at the apex. Too thin, and the jet lacked mass to penetrate deeply. Too thick, and the cone wouldn't collapse efficiently during detonation, wasting explosive energy, accelerating excess copper mass. Morrison picked up one of the copper cones from the inspection bench, feeling its weight in his hand, roughly 100 grams. It looked simple, almost crude, despite the precision manufacturing. Just a cone of reddish metal, approximately 60 millimeters in diameter at the base, its inner surface polished to a mirror finish, its outer surface left slightly rough from the forming dies. But this piece of copper, he'd been told by engineers who themselves seemed uncertain about the physics, was the difference between a weapon that could reliably knock out German Panzermark 4 tanks and one that would harmlessly bounce off without significant effect. The assembly process that followed involved 17 separate stations, each worker performing a specific operation that contributed to the finished rocket. The copper cone was installed. First, positioned carefully in a machined aluminum housing that maintained precise standoff distance from the rocket's nose cap. Then came the explosive charge. Pentalite provided by DuPont's specialized munitions plants, packed carefully around the copper cone with attention to density and uniformity. 8 ounces of it, approximately 227 grams, mixed to exact specifications of 60% PETN and 40% TNT by weight. The packing operation was critical, Morrison learned from the production engineers. Air pockets or voids in the explosive could create asymmetric detonation, causing the copper cone to collapse unevenly and produce a jet that deviated from the centerline. Density variations could cause similar problems. The explosive had to be tamped carefully, achieving consistent density throughout the charge while avoiding excessive pressure that might crack the copper cone or damage its precise geometry. After the explosive came the rocket motor, a solid propellant cylinder that would accelerate the complete round to approximately 82 meters per second during its 1 second burn time. The motor was manufactured at a separate facility, arriving at Bridgeport already loaded with propellant and fitted with an electrical igniter that would fire when the launch tube's battery system sent current through the rocket's trailing wires. The fins came next, 6 aluminum blades riveted to the rocket motor housing to provide spin stabilization during flight. The fins were cut from sheet aluminum, formed to precise angles, and attached with careful attention to alignment. Asymmetric fins would cause the rocket to tumble or deviate from its intended trajectory, potentially missing targets at the weapon's maximum effective range of 300 yards. Finally came quality control inspection, where finished rockets were weighed, measured, and subjected to a series of non-destructive tests checking for manufacturing defects. Approximately 1 in every 100 rockets was pulled from production for destructive testing, fired against armor plate to verify that the batch met penetration specifications. The Army insisted on minimum penetration of 75 millimeters against vertical rolled homogeneous armor at 90-degree impact angle. Anything less, and the entire batch would be rejected. Morrison assembled his 10th rocket of the day, carefully installing the copper cone into its aluminum housing, packing the pentalite around it with gentle pressure from a wooden tamping tool, checking the standoff distance with a depth gauge to ensure it matched the specification of 90 millimeters from cone apex to nose cap inner surface. Each rocket took 17 minutes to assemble by hand. They were building them at a rate approaching 1,000 per day, with plans to increase to 3,000 per day by summer. By the time American forces landed in North Africa in November, they'd have tens of thousands ready for shipment. He wondered if the soldiers who fired these things would ever know that the entire weapon depended on a piece of copper shaped just right, on explosive packed with precise density, on standoff distances measured to the millimeter. Probably not. Men in combat didn't care about the engineering details. They just wanted weapons that worked reliably when they pulled the trigger, weapons that killed enemy tanks before those tanks killed them. Morrison hoped these would, but he'd seen enough weapons fail under combat conditions to maintain healthy skepticism about any new technology, no matter how impressive it looked on paper or in controlled testing. What Morrison didn't know, what the production engineers at General Electric either didn't know or carefully avoided mentioning in their technical briefings, was that the copper cones he was installing were significantly more expensive than the original plan had called for. Army procurement officials had initially proposed using mild steel liners instead of copper to reduce costs and preserve copper supplies for other critical applications. Steel was cheaper, more readily available, and according to some metallurgists' theoretical analyses, should work almost as well as copper for shaped charge applications. Heinrich Mohaupt had warned them back in 1940 that switching from copper to steel would reduce penetration by approximately 30%. His experimental data clearly showed that steel liners produced jets that fragmented prematurely, breaking up into particles that couldn't sustain deep penetration. But American procurement officials, confident that their own metallurgical analysis was superior to the claims of a foreign consultant who was no longer involved in the program, had decided to produce the first batch of M6 rockets with steel liners to see if the cost savings justified any minor reduction in performance. Those steel liner rockets, approximately 15,000 of them, manufactured between February and June 1942, would soon ship to North Africa with the invasion forces, and American soldiers would discover, at terrible cost, that minor reductions in performance mattered enormously when facing German tanks in actual combat. November 14th, 1942. Corporal James Delacroix crouched in a muddy drainage ditch outside the Tunisian village of Medjez el Bab, trying desperately to remember everything the hasty training session had taught him about the peculiar weapon now resting awkwardly on his right shoulder, the M1 bazooka, rocket launcher, stovepipe, tank killer, anti-tank weapon. They'd given it half a dozen different names during the 30-minute crash course, but nobody had bothered to explain to James and his squad how to actually use the damn thing in combat conditions. The training had been conducted by a captain who'd arrived from Aberdeen Proving Ground 3 days earlier, who'd admitted he'd only read the technical manual once himself and had never actually fired the weapon. Load the rocket from the rear, making sure the electrical leads connect to the launcher's battery contacts. Make sure nobody's standing directly behind you when you fire because the rocket motor produces dangerous backblast. Aim at the side or rear armor of enemy tanks, not the frontal armor. Try to hit at 90-degree angles rather than glancing impacts. The captain had mentioned something about shaped charges and copper warheads and hydrodynamic penetration, but it had all been technical jargon that meant absolutely nothing to an infantry corporal from Louisiana who'd been farming sugarcane 6 months earlier and had never seen a tank until arriving in North Africa. What James understood, what every man in his squad understood with visceral clarity, born of watching German panzers support infantry assaults for the past week, was simpler and more urgent. German tanks were rolling toward their position right now, and his Springfield rifle wasn't going to stop them. The bazooka might work, or it might malfunction and kill him. The rumors about premature detonations, about rockets getting stuck in the launch tube and exploding, about electrical systems failing in wet conditions, had spread through the battalion faster than official reassurances could contain them. His loader, Private Eddie Chen, knelt beside him, with a rocket cradled carefully in his arms like it might explode if jostled too hard. Eddie was shaking, whether from fear or the cold November rain or both. James couldn't tell and didn't have time to ask. The rocket looked fragile and crude, its thin metal skin slick with moisture, its electrical leads dangling like loose wires on a broken farm tractor. This weapon was supposed to stop a 30-ton tank armed with a 75mm gun. The Panzer Mark III appeared around the bend in the muddy road, its grey paint darkened by rain, its long-barreled main gun traversing slowly. As the commander searched for targets, James felt his throat tighten involuntarily. They'd told him during training that the bazooka was effective up to 300 yards, but everything in his infantry instincts, learned during weeks of small unit combat, screamed to wait until the tank was much closer. Closer meant better chance of hitting the target. Closer also meant better chance of that tank's coaxial machine gun finding him first, chewing up the thin cover of the drainage ditch with 8mm rounds. 200 yards, 150. Eddie fumbled with the rocket, his hands shaking so badly that it took 3 attempts to get it loaded properly into the rear of the tube, to connect the 2 electrical leads to the battery contacts. James pressed the bazooka tight against his shoulder the way the training captain had demonstrated, lined up the crude iron sights on the tank's side armor, aiming for a point just behind the turret, like the manual said. Weak point, engine compartment, ammunition storage, critical systems. He squeezed the trigger, completing the electrical circuit. For a heart-stopping moment that seemed to stretch for hours, nothing happened. Battery dead, wet connections, faulty rocket. Then the motor ignited with a whoosh that surprised him with its relative quiet compared to artillery. No massive recoil throwing him backward. No deafening explosion rattling his skull. The rocket streaked toward the Panzer, trailing white smoke, spiraling slightly off course from what might have been asymmetric fins or wind or simple bad luck, before slamming into the tank's hull about 2 feet behind where James had carefully aimed. The explosion was anticlimactic, nothing like the dramatic effects shown in training films. No a massive fireball lighting up the battlefield, no turret blown into the sky, no secondary explosions from cooking off ammunition, just a sharp crack and a small puff of smoke that dissipated quickly. James thought he'd missed entirely or the rocket had failed to detonate properly, but then he noticed smoke beginning to pour from the impact point, thin at first but thickening. The tank lurched to a stop. The engine note changed from powerful rumble to coughing stutter and died. The turret hatch popped open and crew members started bailing out, moving with the urgent scramble of men who knew their vehicle was finished. Eddie was already loading another rocket with hands that were steadier now, adrenaline overcoming fear. But the Panzer wasn't moving, its engine silenced, thick smoke pouring from the penetration hole and from around the engine deck hatches. That tiny copper cone, no bigger than a coffee cup, weighing less than a stick of butter, had punched through armor plate that American 37mm anti-tank guns struggled to defeat at this range. The tank was effectively dead, its crew abandoning it rather than risking catastrophic ammunition cook-off. James didn't understand the physics of shaped charge penetration, had never heard of Heinrich Mohaupt or copper liner technology or hydrodynamic jet formation. He didn't need to understand. The weapon worked. The tank was stopped. That was enough knowledge for a combat infantryman who just wanted to survive until the next day. What James also didn't know, couldn't possibly know without access to classified ordnance reports that wouldn't be declassified for decades, was that his rocket had been one of the early production M6 models equipped with the mild steel liner that procurement officials had substituted for copper to reduce costs. Later production runs, starting in mid-1943, would switch back to pure copper liners that would increase penetration by 33%. And the steel liner in his rocket had managed approximately 75 millimeters of penetration, barely enough to defeat the side armor of a Panzer Mark III. Copper liners would achieve 100 millimeters, enough to defeat even the up-armored Panzer Mark IV tanks that were already appearing on the battlefield in increasing numbers. The difference between 75 millimeters and 100 millimeters of penetration, between marginally adequate and reliably effective, would mean the difference between a weapon that barely worked under ideal conditions and one that consistently killed enemy tanks. And that critical difference came entirely from Heinrich Mohaupt's insistence 5 years earlier on using copper instead of steel or any other metal for the shaped charge liner. An insistence that American procurement officials had ignored until battlefield failures forced them to admit he'd been right all along. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.